Now the proofs are all over. Now we will be talking about some application side. What can be the application of these new results which come from Riemann hypothesis and its proof of zeta values? So first thing it came to my mind that immediately after achieving the proof, what new mathematics is going to bring in, and I saw that zeta function is intricately connected with the factorial function and zeta function. Zeta function also is a kind of mm, is a kind of uh, logarithmic function. Logarithmic function in that sense because it has got the form of a derivative of logarithm. Ln of x is equal to 1 upon x, and throughout all the zeta functions, zeta values are all the representations are of the same forms. So when we are summing up those things, we are uh, we are taking the integral of ln of x. So although we know the formula x integration formula, but here we are doing something different. Not it's not only from a calculus approach, but uh, we were stuck in somewhere in the point of singularity or point of or where is the base, main base. So we fixed there. Now we'll be trying something more on the we'll see um, what kind of problems we are having with in our existing mathematics, and how this new information can help us to get out of those problems. So I saw that complex logarithm is kind of a mm, is stuck in somewhere in the in 3 dimension. It doesn't work actually good either way. If you follow the Euler's approach or Riemann's approach, both the way it doesn't work fine. In Euler's approach we need branch cuts. In Riemann's approach, the Riemann sheets, although we can stack it up in higher dimensions, but but this the values of this Riemann's complex logarithm moving from one sheet to another, disappearing from this sheet and reappearing from in another sheet, these kind of inconsistencies are there. So complex logarithm, can you do something with this? And also one more problem is there. Our principal logarithm, that is called ln of 1, the definition of 1 we have set for ln of 1 to be 0. That doesn't hold good in case of complex logarithm. So what's the way out? Here what we have tried here, I have tried to extend the number system itself with the idea from Hamilton's idea of quaternion, and uh, and um, ln of 1, that is principal logarithm of 1, we can see that to be ln of product of 2 minus 1s, 2 minus 1s minus 1 square. So we can here, sorry, we can do one thing. We can keep 1 minus 1 as the in the real world, representing the real number line, and another minus 1 we can see as quaternions, 3 quaternions. Actually we don't need quaternions, but because the first idea came to my mind of using this number system, and I was searching in the internet, and I find this nice piece of work of Mr. Hamilton. So uh, as acknowledgement to that, I will use this quaternion concept only, because vector algebra, although may fit the scenario, but when talking about numbers, we should talk in the same kind of concepts. So vectors are not numbers, no. So yeah, complex numbers can be represented as vectors, um, but numbers is a quantitative thing. So um, so let's better use the quaternion concept. But we will see that in the quaternion, here I have mentioned it, the quaternion algebra, the quaternion Hamiltonian product, when we take the big formula what he suggested, actually melts down melts down to just an addition formula, in case this all these cross products are zero, and that will happen in case the the quaternions are placed at parallel or zero. So the unit disk, unit circle concepts. Okay, let us, before we go there, so let us do these things first, then it will be clear. What we have tried now, we have tried to redefine the unit circle. There is a unit circle called z is equal to e to the power ix. I know, we know, everybody knows. So I am proposing another kind of unit circle, uh, another kind of half unit circle. Modulus of z is equal to half e to the power x, ix is equal to 1. So this is possible because in the derivative representation of this unit circle unit circle concept of Euler's exponential form, if we set the initial value to 1 and r equals to half, then ix must turn out to be ln2. Ix turned out to be ln2 in natural real sense. Then it will have a total real kind of thing, which is well understood. But we need to understand that this real kind of thing is happening actually in 4-dimensional system, with the background of background of 4 quaternions acting behind. So in that case, how the unit circle will look like, I have not written the draw the circle, but projected it to the unit sphere, and it will look similar to the unit sphere what Riemann did, but only 2 parallel surfaces will be coming. One up, the one unit surface will be coming in the equator, then half unit surface will go to the southern hemisphere. The south pole will be representing 0, north pole at infinity, and the d unit sphere surface will be sitting in the north hemisphere. And one more good thing, because we have discussed quaternions, so they will be in constant rotation. So this we can see this whole unit sphere rotating around itself, and also along with that there will be some complex rotation of this kind, these surfaces also. So there will be rotation of the surface. When you see the conic sections, they will look similar to this drawing. Okay, now coming to this log, we have tried to represent this -1. Here it is little bit different thing is written. Okay, not to, I will edit this afterwards. But what we can do, -1, we can write as I j k, 3 vectors, because that's the formula given by Hamilton when he extended this quaternion concept. He actually the very next day, um, he was walking by the bridge, some bridge, and he got these revelations that he can do this for 4D kind of mathematics once he introduced some more number systems. And because without that he was not able to finish this 3D, although after that some hacks were found on, and vector algebra has given us has worked well in R3. But for higher dimensions, quaternions work better than vector algebra, because it takes into account all the minute details of rotation. That's why rotation algebra, whenever it comes to about rotational matrix or sometimes some mm, some complex rotation issues, then we rely upon Hamilton's work. So this I and ijk we can either see as a vector, because my unit disk and unit surfaces are sitting parallel to each other, so we don't need much rotation matrix, but it is always there in the complex one, because there may be some issues sometimes. It may not work that time. We need to bring those concepts back. mm, yeah, so I was talking about the principal logarithm. We are fixing it, and -1 we have kept it 1 minus 1, sorry, one set of -1 we have kept for this thing called real world, negative real side, negative of the -1, and another negative one for ijk. Ignore this part, ln of I square j square k square, that part you ignore. We can see this ln of ijk. So the final result will be, because we can take with this form also, that will be also true. But or rather later I realized that when I saw this parallel kind of thing, actually then I realized that our normal vector will be sufficient. We don't need quaternions to fix this concept. But we need to keep in mind that our quaternions are always there. So this unit vectors, 3 unit vectors, sum of 3 unit vectors can be 0 when only at 2 pi by 3 angle. That's the thing actually we got from Riemann hypothesis. We saw there zeros, zeta zeros falls on pi by 2, pi by 3 angle. Here we are saying it is 2 pi by 3. Okay. Now this quaternion logarithm. Quaternion logarithm, there is a nice property, nice theorem I put forward, which talks about the modulus of ln. If we take natural logarithm of natural logarithm or any sort of logarithm, any base logarithm. On the quaternion system, complex logarithm, then the modulus of that logarithm will be equal to modulus of another quaternion, which will be a representation of the just planes addition form of the real numbers, um, and the and its complex or components like I, j, k. If we take the real coefficients and add them up, then we'll get another quaternion representation, and the product, original product, although the original product will be something else and this will be something else, but their modulus is going to be the same. How? Let's see the proof. Let us take a series of the quaternions, infinite series, q1, q2, q3, and let us represent it by real numbers into pieces, into the imaginary components I, j, k. Then when we finish up this all the multiplication, then we will be exhaustively using this all the real numbers or natural numbers, whatever. I have just used the real numbers. We can use the rational numbers, even irrational numbers. No, irrationals are not, but so pluses or minuses, all the natural numbers can be used here. So now if we take the ln, you see that some product to sum form will be applicable, and it will be turn out to be ln1 plus 2 ln2 plus ln3 plus ln4, like this thing will happen also in the um, imaginary parts ijk. Then if we that will be applicable to infinity, but because we have seen that zeta function has got analytic continuation and it's a holomorphic function, uh, we can cut into pieces, we can truncate the series, and we can take partial sum, whatever we want we can do it, and in that sense we will get it. This whole formula will work for 2 quaternions, 3 quaternions, 4 quaternions, as many numbers as you want. We have got it. This formula has got some corollary also, which is nothing but the exponential form, and because it is applicable to q1 plus q2, q1 plus q2, we do the quaternion regular vector addition. In that case also, in that case also mm, in that case also it will be true. No, here okay, I'll look after this. Yeah, it should work in addition also, addition and subtraction, both the cases. Now we have seen that quaternions actually is indicating something real, real numbers. So can we do the projections? Can we do the projections with the help of some kind of guidance from the unit concept, and project the concept of unity to some real numbers? uh, representing a complete cycle or some kind of. So that was my idea, and I started with the initial value of ln2 that I already discussed, and I got this nice, what I should say, it's kind of Euler's identity, the e to the power I pi plus 1 equals to 0. Similar to that, I got these kind of identities, like 1 upon e is equal is e 1 upon e plus ln of I is equal to 0 is equal to the reverse also, e plus 1 upon ln I. And because we have defined I square equals to minus 1, that when you plug minus 1, that ln minus 1 will be 2 ln of 2 of ln I. Now if we project this to the exponential form, then we will get some values. Here the first one is giving 2.177, and if I take unit partitions of this further, then it will give some more constants. Similarly, second quaternion will give us, second quaternion I found this one, 1 upon pi minus 3, which again reset the value of pi is equal to 3 plus 1 upon I. So pi, in that sense, pi is a complex number too, because from the quaternion side, the decimal part of pi which does not end ever, so that is due to complexity, some complexity in higher dimension. So rational numbers are kind of a complex numbers. Irrational numbers are kind of a complex numbers. Okay, we are getting nice, interesting results, and the Euler's kind of identity will be in this case will be ln I minus 2 equals to 0, and 1 upon ln I minus half equals to 0. Similarly, it will be minus 2 of ln I. When you project this to some real number line, it is getting projected to a big jump from e to the power 2 to e to the power 22. It's almost 10 multiples, 10 orders of magnitude. So it is giving us a new number system which sits always on the top of e, and it's a decimal system because we are based on thing. We are in based on thing, so we will be getting all the 10 orders of magnitude. So how quick this scale is moving. Earlier it is also it is kind of a addition, the 1 plus 2 plus 3 plus. Here also the same addition rule is happening, 1 plus 2 plus, but it is sitting on the top of the base e. That's the difference. So it is much more faster than the number sequence we generally follow in the real number line. So it has given us some kind of rotation, and all the numbers 1 2 3 will have this kind of representations. I didn't try it anymore because I got the pattern. So next theme it will come, we can guess around 33, and the pattern will be continuing up to infinity. So as high we want to go, it will go the same direction. Now some mysterious thing we encountered here, how pi is appearing here. So that I looked into, and I found that pi can also be represented as a base of logarithm. How can I do this? Here we need to do some bit of manipulation on the formula of pi and ln2 both. So when you split the ln2 formula into two parts, then mm, let me have a look. Basically, here what we have done here, we have just taken this factorial forms. We have written it in the factorial forms. Then we have introduced the I for changing of signs at odd values. Here changing of signs at even values. Then this part is going to a geometric series. Then we are doing the some kind of algebraic operation. Then we are defining as sine I plus cos I, this part to be pi again. Then now we are replacing this pi by pi minus 2 equals to ln of pi, because both the side we need to go for exponentials, and there one more pi is hitting there. So ln of e to the power pi by 2 by 4, if we take both the side ln, and divided by ln of pi is equal to 1 upon pi and pi to the power minus 1. So if we set this ln by 2 part is equal to pi to the power some complex number pi to the power j e, then whole thing comes into pi to the power j e is equal to minus 1. Some head spinning techniques. Yes, because I was quite sure that I will get a form, then I I somehow hacked it. I cooked it because I was quite sure, because there has to have some symmetries. It was giving me a hint, so I applied that symmetry and it's shown me. Then the simplified complex logarithm is also applicable on complex numbers also, z1 z2 z3, the same thing what we have done in case of quaternions. On the closure property of real logarithm, on the real logarithm number line negative logarithm was undefined. Now we can define as follows: ln minus 1 to be 0 as in principal logarithm, and ln minus 2 we can define this way, equals to ln of half, and this ln 2 plus minus ln minus 2 equals to 0. This will also implies that ln 2 minus ln 2 minus ln minus 2 is equals to 2 of ln 2. That's kind of a addition, minus addition, so it is getting plus. Ln 2 divided by ln of minus 2 is equal to minus 1, kind of multiplicative inverse but negative inverse, and we can get also ln 2 into minus ln 2 equals to minus ln 2 whole square. So regular minus with the minus sign, as a regular multiplication with the minus sign. This way we can close the negative logarithm and real logarithm. Also complex logarithm is also fixed. Now with the total picture comes that with this whole thing, logarithm is closed under a system of quaternions. We must say it's not complex number, it's actually basically it's four base number system. Similarly, we can fix the issues with factorial functions also. Factorial functions, we know that it is, although negative factorials are defined, but there is no functional representation for that. And we have just discovered one function called delta function, which has got the depth of handling this thing. So we'll be using those things. Mm, Gamma of rational numbers is already defined, is capable, gamma function is already capable of doing the rational numbers factorial. So that way we can leave it there. Only we need to fix the negative part. That's the limitation of factorial function. So for that we will be doing the same thing. With this part you might have seen earlier. We have just discussed in the proof of Riemann hypothesis that delta gives this values. Delta minus 1 is equal to minus 1, delta minus 2 is equal to minus half, delta minus 3 is equal to minus half, delta minus 4 equals to minus 1 upon 12, delta minus 5 is equal to 1 minus 1 upon 24. So there is a continuous minus value there, so minus sign there, and it's proceeding in the sequence of some even number series 2, 12, 4, 24, and then 240. The jumps are not regular. Um, it's similar to the factorials only, because factorial 3, I think 3 into 2 6, double of that is 1 upon 12. Then factorial 4 is equal to 4 6 is 12, 24. Yes, 4 6 is 24. Factorial 5 is equal to 5 24 is equal to 120, but here it is 5. Oh, factorial 5, which okay, we need to see there is a shift, minus 1 kind of thing is there. So we'll be, when defining the factorials for negative values, we have to be careful. We have to give two separate definitions, two representations, for one for the even numbers, one for the odd numbers. So negative factorials, when we, for odd numbers, for even numbers, will be minus 1 upon this, minus 1 upon delta minus minus n minus 2. But how can it be? There is something wrong here, maybe, because minus 1, if it is there, how the sign will get changed? Because I know Ibrahim has defined the factorial functions to be negative factorials to be considered as the product of all the negative numbers of that number whatever we are taking the negative factorial up to negative minus 1. So in that sense, factorial will have always an alternate sign. We need to, okay, this alternate sign, how we will be getting here? I think I have committed a mistake. It should not be minus 1. It should be 1 upon, just simple 1 upon. I'll remove those minuses, and if we take the reciprocal, then it will give the factorials. And for positive numbers, it should be 1 minus n plus 1 should be added, sorry, multiplied. And that's all. With this we can define the negative complex numbers also. For example, here we have calculated this one, I minus 1, from the initial definition of this whatever, gamma of 1 plus I, we know this value already. So applying this new concept, new value, we can do the same thing here. Okay, that's all, and we'll see in next video.